Hello students, in this video we will discuss about the numerical problems of chemical kinetics. Now these are the some solved examples and some unsolved questions we will discuss. This is the one example of your textbook 4.2. The decomposition of N2O5 in CCl4 at Kelvin has been studied by monitoring the concentration of N2O5 in the solution. Initially, the concentration of N2O5 is 2.33 mol per liter. After 184 minutes, it is reduced to 2.08 mol per liter. The reaction taking place according to this equation, and we have to calculate average rate of the reaction in terms of hours, minutes and seconds, and what is the rate of production of NO2 during this period. Now see, average rate, this is the formula of average rate. Clear? This y minus, because we are taking the concentration of reactant, put the value. This is the change in concentration. This is final concentration minus initial concentration. This term will come negative, and when this negative is multiplied by negative, we will get the positive average rate. Okay, we will solve it, then we will get this one. This is in mole per liter per minute. Now we have to convert this per minute into per hour. Then this is multiplied by this unit factor. If you remember in class 11th we have discussed. Okay, then we will get this is mole per liter per hour. Again, when we have to convert this per minute into the second, then this is the unit factor, multiply by this, we will get this in mole per liter per second. Okay, now important thing is we have to determine the rate of production of NO2. Now see, according to this equation, what is the relationship between the rate of reaction and production? This is the 4. That is, rate of reaction is 1/4 of rate of production of NO2. Or we can say rate of production of NO2 is 4 times of the rate of reaction. Clear? Now see, in this case, this one is given. Rate of reaction is 1/4 of the rate of production of NO2. And the rate of production of NO2 we can find, this is the 4 into rate of reaction. Put the value and we will get final result. Okay. Now this is the calculate the overall order of reaction which has the rate expression. As we know, in rate of expression you have to simply add the powers. This is half plus 3/2. This will be equal to 2. That's why this is second order reaction. In this case, this is 3/2 and this is -1 if net result is half order. Okay. Identify the reaction order from each of the following rate constant. Rate constant is given. Okay, then how can you find out the order of reaction? Just from its unit. Remember, from these units we have no meaning from this magnitude, only see unit. Actually, this is 10 to the power -5 and this is 10 to the power -4. This is the unit, liter per mole per second. If you remember, this is the unit for second order reaction. And this is second inverse. This is the unit for first order reaction. Clear? Important numerical is there. The conversion of molecules X to Y follows second order kinetics. If concentration of X is increased to 3 times, how will it affect the rate of formation of Y? Dear student, this is the one of the important numerical from this chapter. Now just see, first initial rate, this is given. Actually, this is the second order kinetics, that's why power 2. Now if concentration X is increased 3 times, then its rate becomes R2. Simply concentration, this is 3x. If we solve it, we will get this one. And if we take the ratio of these two, then we will get 9. It means rate of formation of Y will increase 9 times. Now next example, initial concentration of N2O5 in the following first order reaction. This is the given, and this is the concentration is given. This temperature, concentration of N2O5 after 60 minutes, it remains there. Okay, and you have to calculate the rate constant. Now what are things given? Initial concentration is given, concentration after time, that is R, is given, and time is T60 is given. And this is the formula for the first integrated rate equation for the first order reaction. Okay, and in this case K, rate constant, how can we find out? Actually, in this case, what we can say, the concentration, put the value 2.303, 60 log. This is initial concentration, this is final concentration, and when this come to the log 6.2, this is again important, dear students. You have to find out the log 6.2. We have in one of my video of electrochemistry, I have explained in detail how can you find out the log. Before decimal, there is a one digit is there. Reduce one digit, that's why we'll get the 0. Then you have to see the value of 62 in 0. 62 in 0. See, this is 62 and this is 0. That is 7924. This is put 0.7924. If we solve it, we will get this one. Okay. Don't forget to mention the unit. Okay. Next one is. Now again, these data were found during the first order thermal decomposition of N25. Thermal decomposition of N25. Reaction is given like this. Time 0, total pressure is 0.5 atmospheric pressure. When time is 100 seconds, this pressure becomes 0.512. Calculate the rate constant. Actually, this is the gaseous reaction. Okay. Now see. This at when time t is equal to 0, initial pressure is 0.5 atmosphere, and this pressure is due to only N2O5. Okay, and this is 0 and this is 0. When time becomes t, then we can say when it's a 2x atm pressure is reduced. Why this is 2x? Because its stoichiometric coefficient is 2. Okay, then we can say 2x atm pressure of N2O4 is formed, and this is x atm of O2 according to the stoichiometry equation. Then we can find P total is P N25 plus N2O4 plus PO2. Put the value, and from this we can find out X. Okay, this is we can find out the X. And pressure of N2O5, pressure of N2O5 after time t, this is 0.5 minus 2x. Okay, 2x. Put the value of x, then we will get this one if you solve this one. Okay. Time is 100 seconds. Total pressure is 0.512 atmosphere. That's why we can find out this is P and 205 is 1.5 minus 2 into. This is the total pressure point. This is given in the question. This is the pressure of N25 after 100 seconds. Now put the value in integrated rate equation of first order, this one. Now in this case we are taking the partial pressure. This is the initial partial pressure and this is the partial pressure after certain time. Put the value. Again you have to solve this log. Okay. Before decimal there is one digit is there. Reduce 1, that's why we'll get the 0. Put the point and now see 10 into 5. Value of 10 in 5. Just see. This is 10 and this one 0 2 1 2. Okay, this is 0 2 1 2. If we solve, we will get this one. Now next, a first order reaction is found to have a rate constant is given. Find the half-life of a reaction. Very simple question. Very simple question. This is the relation between T half and rate constant. Put the value and we will get this one. Again, don't forget to put the unit. Show that in a first order reaction, time required for completion of 99% is 10 minutes to half-life 10 times, sorry. 99.9% is 10 times of half-life of the reaction. So for 99.9% completion, from this we can say if initial concentration is 100 and this is completed up to 99.9%, it means how much remain? This 100 minus 99.9, that is 0.1. Okay, so we can say this is, put the value again, integrated rate equation for first order reaction. Initial concentration is 100 divided by 0.1 and we can find out the log 10 to the power 3. You can say this is 3 come first, log 10 value is 1, that's why we will get this one. Okay, this T is equal to 0.6909. again remember this one. Okay, this is the time for 99.9% completion, and for T half this is the formula. Then take the ratio of these two, this will come 10. Okay, Now, a first order reaction has a rate constant. How long will 5 gram of this reactant take to reduce to 3 gram? This is again one of the important category for the numerical of chemical kinetics. That is, initial concentration is given, final concentration is given. You have to find out the time in which this concentration is changed. So we can say this is initial, this is final, this is integrated rate equation for first order. Put the value log 5 by 3. If we solve 5 by 3, then we will get 1.667. Now see the again logarithm table. Before decimal, there is the one digit is there. Reduce 1, we will get 0. Put the decimal, then you have to see 16 in this. This is 16. Okay, then 6, this is 0, 1, 2, 3, 4, 5 and 6, this is 2, 2, 0, 1. Okay, then fourth digit, what we have to do, fourth digit, this is the main difference. Then 1, 2, 3, 4, 5, 6 and 7. This 18 we have to add in 2201 and this will come 2219. Solve it, we will get this one. Okay. Now, next, the rate constants of a reaction at 500 Kelvin and 700 Kelvin are this. Okay, this is for 500 Kelvin, this is for 700 Kelvin. And you have to find out the value of activation energy and value of A. This is based on the Arrhenius equation. We are having this formula, log K2 by K1 is equal to EA by 2.303 R, 1 by T1 minus 1 by T2. Everything is given. T1 is given, T2 is given, K1 is given, K2 is given, and you have to know the value of R, 8.314 joule per Kelvin per mole. Put the value. Okay. Now again put the value. Again come, this is log 3.5. How can we solve it? Before decimal there is one digit. Subtract 1, we will get 0. Put the decimal. Then you have to see the 35 in log table. This is 35 in 0. 5441. This is 5441. Put the value on, solve it. This will come in joule. Okay. Then we have to find out the value of A. Again use this equation. Okay. This is a natural log. We have converted into the basis of 10. Okay. And from this we have to find out the log A. So we have rearranged this. Log A is equal to log K plus EA by 2.303 RT. Now this log A is equal to K. This is K. For any temperature we can take either 500 or 700. I have taken for 500. This for 500 K is given 0.02 plus this EA we have calculated already. This is 2.303. This is R and this is T. Then this is log A is equal to this. This can be written in this way, log 2 into 10 to the power minus 2. And if we solve this term, this complete term, this will come 1.905. This is log A is equal to, value of log 2 is 0.3010. I think it's not necessary to see the log table. I think you have understood that you have to see the log 20 in 0. Simply see this is log 20 0, 3010. Okay. This is by minus 2. This is 10 to the power minus 2. If we take the log of this will come minus 2. And if we solve it, this will come log A is equal to 0.206. Then A is equal to anti-log of 0.206. Now how will we see this anti-log of this? Again see anti-log table start from decimal. So we have to see the value of 0.20 in 6. 0.20 in 6. This is given in the anti-log table. This one is 0.20 and 6 1 where this is 0, this is 1, this is 2, this is 3, this is 4, this is 5 and this is 6. This is 1607. Clear? This is 1607. Okay. This is the value of 0.206. Then what to do? Put the decimal before one place of left side. And then this is multiplied by 10 raised to the power. Now this digit, this number, this is 0. And 10 raised to the power 0 is equal to 1. That's why this is 1.607. Clear? Now next one is the first order rate constant for the decomposition of ethyl iodide by the reaction. This is given ethyl iodide C2H55 if decompose C2H4 plus Hi. Temperature is 600 Kelvin. This is given. Okay, this is the rate constant at 600 Kelvin is given. Energy of activation is given in kilojoule per mole. You have to find out the rate constant of the reaction at 700 Kelvin. Okay, T1 is given, T2 is given, K1 is given. We have to find out the K2. R is given. Again remember, R is in joule per Kelvin per mole. That's why EA, which is given in the kilojoule, we have to convert it into the joule. Okay, now this is our basic formula. Log K2 by K1 is equal to EA by 2.303 R 1 by T1 minus 1 by T2. This can be written as log K2 minus log K1. Clear? Now we have to find out the value of log K2. Okay, we rearrange this, put the value. K1 is 1.60 into 10 to the power minus 5 and everything is given. EA is given, put the value, and if we solve it, this will come minus 2.196. This is the log K2. We have to find out K2. If we take the anti-log of this, I think you are comfortable with the log and anti-log and you can solve it. Okay, thank you very much. Subscribe my channel to get the new videos.